Welcome back to physics. Today I want to go into a couple of things, including electrical potential energy and electrical potential. A couple of words that are very similar, but they have very much different uses. Again, we're getting into fields now, so we're describing fields in ways that we haven't in the past. Fields are interesting things. They have the capacity to interact at a distance, and it's a bit of a magical effect how they do this. But we're going to figure out how to describe that. So interesting, a useful place to. All right, let's look at fields. We'll use gravitational fields as a first example. So as a reminder, if we have two masses, say this is Earth and say this is something else, I don't know, a moon, and they're separated by some distance here between the centers, of course, radius r, that we know a couple of things about this. So first thing we know is that there's going to be some gravitational force of attraction, and according to Newton's universal law of gravitation, this is going to be the product of the two masses divided by the square of the distance. Remember, we had a different way of describing this, right? So fields are really interesting things. So these two masses will interact no matter what's in between them, right? They're not touching, but they're interacting at some distance in a kind of a magical way. So no matter what I put in here, I could put a charge, I could put a mass, I could put a magnetic field, I could put anything in between here, and it will not affect the interaction between these two. So they truly are acting at a distance. And we have a couple of ways of trying to describe this. Right? One way how to describe this, we say, well, what's going to be the force of gravity per kilogram that I'm going to experience, right? So this is one way of describing the gravitational field, right? So my gravitational field, I call this lowercase g, is going to be the force of gravity determined per mass. Right? Well, you should recognize this as Newton's second law, but also you should know that on the surface of the Earth, this is going to be 9.8 meters per second squared. Right? So this is one way of describing a gravitational field. And we're accustomed to using this, but we haven't really described it as a function of the field. We said this is acceleration due to gravity, right? That's what you experience if you put a kilogram there. So you experience 9.8 meters per second of acceleration, or if I put a kilogram there, I'll experience 9.8 newtons of force. Another way of describing a field, which is going to be the force divided by the mass. So the second thing that we got into for gravity was looking at gravitational potential energy. So gravitational potential energy is the product of the two masses times a constant divided by the distance between them, not squared. But there's some important thing here, right? So remember that as I get closer, I start having less gravitational potential energy, and I'm going to get converted to kinetic energy, right? So if I drop something, it's going to accelerate towards the center of the Earth. And that acceleration is something that we can describe as an energy conversion. So the gravitational potential energy we can describe with this negative sign, which makes the math work out. So we set our 0 point at being infinitely far away. And as we get closer, we end up having less potential energy, right? So if I drop something towards the center of the Earth, it's going to accelerate, and I'm going to have less and less potential energy and more kinetic energy. The negative sign allows that to work out mathematically, right? So what's less than 0? Well, less than 0 is going to be -1. Less than -1 is -2. As I get closer, it becomes more negative. So we can describe this. We don't do this, but we could describe this in terms of the amount of potential energy per mass, right? So just like we describe our gravitational field here in terms of the force that could be experienced per mass, we can describe a gravitational potential energy in terms of the amount of potential energy per mass that might be experienced. And this is what we're going to do with electrical fields, but we could do it with gravitational fields. We just don't do it. So in which case I'm going to end up with potential energy per mass, which is going to be this. And the way I think about this is the possibility to have potential energy, just like this is the possibility to have force. We don't have a name that I'm going to use for this, but it is the possibility of having potential energy. And so we're going to switch to in electrical systems. That we're going to describe the field. And we're going to have these same two ways of describing fields. We can describe it in terms of the force that might be possible, and we can describe it in terms of the potential energy that would be possible. And these are the two ways that we're going to get to in just a minute. Okay, analogy. Water analogies are pretty good for thinking about charges and electricity. Okay, here's a dam. So I have a lot of water that's beyond there. Some important things about my dam. So notice if I have a kilogram of water here, that potential energy that it has, the gravitational potential energy it has, is going to be less than the kilogram of water that's up here. So this kilogram of water has some more gravitational potential energy, I can convert more of that to electricity if that's what I'm doing in my turbine here. I can convert more of that and get more energy out per kilogram. So when I'm figuring out the energy that's contained in my dam, the height is really important. So if I have a lot of water up at the top, I get a lot of energy out. If I have a lot of water but it's all low, right, I don't get as much energy out of that. So in terms of gravity, we describe this as right on the surface of the Earth, mgh, right? So mass varies the height. So that's the potential energy that I can have stored. And what matters is the height. If I was to describe this in terms of potential energy per mass, right? So per kilogram, what matters is my gravitational field I'm in and how high I am from my 0 point in this gravitational field. So electricity, we're going to describe the same sort of way, right? So I have my electrical potential energy, and I'll describe this as K Q1 Q2 over R naught squared. My voltage is going to be the amount of potential energy per charge. So, so the analogy that the voltage is describing, or it's my gravitational field, but not only my gravitational field, but how far it is from my 0 point. So my voltage is describing roughly the amount of energy per charge that I can get out, just like my, just like the height of my, just like my gravitational potential energy is describing the amount of energy per kilogram that I can get out of my system. If I have a taller dam, it's going to be pushing more energy out. If I have a shallower dam, it's not going to be pushing much energy out. And voltage is the same idea, but now in terms of charges. So let me flip this around and think about charges. Okay, let's think about voltage a little bit. So if I have a pile of charges here, and a point that I'm interested in, pile of charges and a point that I'm interested in. So this is some distance away. I'll call that R. And if I have more charges the same distance away from a point, which one of these has more electric potential energy? Which one of them has more voltage? So hopefully you're recognizing that if I put a charge here, I would then have some potential energy. If I put the same charge here, I would have more potential energy because this has a larger charge. Similarly, in terms of voltage or electrical potential, that if I put a charge, if I have a point here in comparison to these charges and a point in the same distance away, I have more charges, then I'll have more electrical potential. So let's expand about this. So what if I have a bunch of negative charges, right? In the same distance away here. So here I have positive charges. I have the same number, but of negative charges. How is the voltage? Well, hopefully you recognize that the magnitude of the voltage is going to be the same, but the sign is going to be different, right? So my voltage, I can calculate as KQ over R. And so if I have a negative charge that's generating this electrical potential, I'll end up having a negative value for voltage. And if I have a positive charge generating a electrical potential, that now I'll have a positive voltage. So oftentimes what we worry about is not the absolute voltage, but we're going to look at the change in voltage, especially when we're dealing with things like batteries. We're going to have an electron that can flow from a negative terminal to a positive terminal. We're not worried about the absolute value of voltage, but we're worried about the change in voltage. So in this case, right, so V final minus V initial, my change in anything is going to be final minus initial. So if I'm flowing from an area of high potential to low potential, that my change in voltage is going to be right, my KQ over R, where Q is positive, minus KQ over R, where Q is negative, and I'm going to end up with my magnitude is going to be twice KQ over R. So if I'm flowing, so this is how we're going to worry about my electrical potential. So if I'm flowing from a positive to a negative, right, my change in potential is going to be very significant. If I'm flowing from a positive to ground, to a neutral, then my change in potential is going to be less. So this is how we're going to use batteries. And this is what we're doing with batteries, essentially. We have a pile of negative charges at one side, a pile of positive charges at the other side, and we're letting the electrons flow from the negative to the positive. Remember, currents flow in the opposite direction. Sorry about that. But we're going to have this flow, and that is essentially increasing the height of my dam, right? So I get more energy, I have the possibility of more potential energy to flow from having a bigger pile of negative charges. So what we worry about a lot is the change in electrical potential, or the change in voltage. A few interesting things about electrical potential energy and electrical potential, or voltage. So imagine here I have a positive charge in a point some distance away. So we could figure out what the electrical potential is. If I put another charge there, I could figure out what the electrical potential energy is. If I put a negative charge the same distance away, so we'll call this R and this R. So I put a negative charge the same distance away. Notice what happens, right? So my electrical potential energy, right, is going to be purely additive. So I'm going to have the potential energy from the 1 plus the potential energy from the 2. But notice that my charges are different here. So whatever this charge is here, I'm going to have these will be opposite signs, and if the magnitudes are the same, it'll add up to 0. The same is true with my electrical potential, or my voltage. The electrical potential is going to be simply additive, so I'm going to have the voltage from one plus the voltage from the other. And if these two charges are equal in magnitude, then I'll end up having a voltage of 0. Kind of odd to think about that I can add together potential energies and get a 0, but it's really important that the signs are involved with this, right? So I'll have some potential energy, whatever I put here. Say I put a positive test charge here. Put a positive test charge here. It's going to be attracted to this one. It's going to be repelled from that one, right? The net effect is going to be 0. Notice this is not true for forces, right? So my forces are going to be a little bit different, because my forces have to take into account the direction. So my forces in electrical fields are vectors, right? Direction matters. Potential energy and electrical potential, or voltage, are scalars. So there is no direction that matters. They're simply additive. Electrical forces and electrical fields, I have to worry about the direction as well as the magnitude to make an influence, right? So if I put a positive test charge here, it's going to experience some net force. Right, it's going to be repelled and be attracted, and it's going to experience a change in electrical potential and electrical potential energy. But the starting point for this is that the electrical potential energy would be 0, and my electrical potential would be 0 at the start. Remember, this 0 is sort of random, sort of human-made idea that I can have less than 0 potential energy. I've just decided, well, I'm going to add these together and make this equal 0. Right? So I can have less than 0. So I'll have something, if this starts moving, I'll have converted potential energy into kinetic energy. And I'll have less potential energy, right? So I'll have negative potential energy. And that's okay, because this is not an absolute measure. It's not measuring the absolute amount of energy that's available in the universe. It's just my 0 point that I've decided arbitrarily. Okay, last thing I want to mention about electric potential is what happens in circuits. So this is our description of what a battery looks like, and on the long side I'm pretending I have positive charges. On the short side I'm going to have some negative charges. It'd be the same number there. Did I draw the same number? Yeah, pretty close. Then we're going to connect this with a wire, and it's going to go through something and come to the other side, right? So I'm going to make this as a resistor. I'm going to put glass around it, and I'm going to call it a light bulb. So now I've made a little circuit that has this battery. So what a battery is doing, a battery is taking electrons and is pumping electrons in this direction, right? It's saying, oh, I got an electron here. I'm going to move it to the other side of my battery. And what happens, my electrons are going to flow in this direction. And unfortunately, in practice, we think of current, or we define current as being the flow of positive charge. Doesn't really happen. My current is going to be the flow in this direction. What a battery is doing, though, is taking that charge, those electrons, and pumping it this way, or if you want to think of it, and it's pumping the charge in the opposite direction. So my battery is providing some energy. It's providing potential energy. And the way that we define this, we say, well, this is describing it as define it as providing some electrical potential. So right, my voltage, you've heard of 9-volt batteries or 12-volt batteries, like in a car. So I have some voltage, which means that if I had a charge, that would have some energy associated with it. So I could think of it as an electrical field being set up in this wire. So I'm setting up an electrical field in this wire. And if I have a charge here, that charge is going to have some electrical potential energy. Right? So I have a charge in an electrical field. And this is basically what we're doing. So we're setting up an electrical field, it's in a wire, and we have some charge, we're going to sort of push it. And the way you want to think about voltage, right? So voltage is how hard that charge gets pushed. So it's the height of the dam, right? So my voltage are going to push charge. They're going to, just like the height of my dam, the higher the dam, the harder the water gets pushed out the bottom of it. And just like the larger my voltage, the harder that charge gets pushed. Right? And what happens to that depends on what's going on inside the circuit, and we'll get into that later. But my voltage is what's going to push that charge. It's not actually doing anything. Right? So this is important to recognize. So that 120-volt outlet that's in your house is not doing anything. It has 120 volts there, but it's not doing anything until you plug something into it. Just like my battery here, my 12-volt battery is not doing anything until I connect it to something, and then stuff happens. So voltage, again, it's the potential to have energy, but it is not the actual use of energy, conversion of anything. Anyway, hope this is helpful, and talk to you soon.